Welcome to the Explainer. Today, we're taking a really rigorous but honestly fascinating journey straight through the building blocks of calculus, right here on our virtual academic whiteboard. If you've ever found yourself just marveling at the hidden mathematical architecture of the universe, well, you are definitely in the right place. We're going to unpack the exact tools that make calculus such an incredibly powerful language for describing change.
So, what connects the geometry of areas to the physics of motion? It's kind of a provocative question to set the stage, right? Because before calculus, calculating static areas and tracking dynamic motion were totally different disciplines. They didn't really talk to each other. But calculus mathematically bridges these seemingly distinct worlds, proving that they are fundamentally just two sides of the exact same coin.
Okay, let's dive into this. Here's a quick mental map for our progression today. We'll start with the fundamental calculus bridge, then move into unlocking U-Substitution, hitting the advanced integration toolkit, exploring geometry and real applications, and finally looking beyond basic calculus.
Section 1. The Fundamental Calculus Bridge, Connecting Derivatives and Integrals.
You know, once we establish this underlying theory that links these two operations, we can practically abandon simpler ideas like the mean value theorem altogether. Let's look at these rigorous definitions. The first fundamental theorem of calculus states that the derivative of an integral is just the original function. Think of it like this. If you integrate a function, and then you turn around and differentiate it, you literally get right back to the exact same place you started. It's a perfect loop. And the best part, there's no plus c to worry about here, because the derivative of any constant simply washes away to zero. Then we have the second fundamental theorem, which states that the definite integral of a rate of change gives you the total accumulated change over an interval.
I actually want to read this profound, yet surprisingly plain English translation straight from our sources. The accumulation of a rate is given by the change in the amount. This is absolutely crucial. If you integrate a velocity function, which is a rate, over time, you are directly calculating physical displacement, the amount. Think about it. If you throw a ball straight up into the air, it travels a huge distance up and then all the way back down. But the definite integral of its velocity, that just gives you the clean, final difference between its starting height and its ending height.
Moving right along to Section 2, Unlocking U-Substitution, Reversing the chain rule.
So now we're shifting gears from pure theory to the actual algebraic mechanisms of solving these integrals. U-substitution is our primary weapon to essentially undo complex differentiation. It is quite literally the reverse of the chain rule. Let's walk through these 4 steps together. First, you pick your u. This is usually the inside part of a composite function, like the stuff inside a radical or raised to a power. Second, you differentiate that u to find du. And remember, you might have to multiply or divide by a constant to make it match your integrand perfectly. Third, you substitute your u and du into the equation. This step is like magic. It turns a terrifying integral into a super simple one. Then you just integrate. Finally, substitute that original x value right back in for u. Honestly, this process makes abstract algebraic manipulation feel completely logical.
Now, what's really interesting about this is a fascinating shortcut for definite integrals, the ones with set boundaries. By changing the integration limits explicitly to u values right at the very beginning of the problem, returning to the original x variable at the end becomes completely unnecessary. No way, right? You just evaluate the integral right there with your new u limits. It is so much faster and far less error-prone than doing all that back substitution.
All right, Section 3, Advanced Integration Toolkit, expanding our methods.
Because let's face it, a simple U-substitution just isn't always going to cut it, so we really need to expand our methods. First up, we have integration by parts, which brilliantly reverses the product rule. You probably remember its famous formula, the integral of u dv equals uv minus the integral of v du. We often execute this via repeated reduction formulas to break down those stubborn, high-powered functions, like say sine to the power of 10. Next, we have partial fraction decomposition, which is a lifesaver for dealing with complex rational expressions. And of course, inverse trigonometric substitutions, which we use to elegantly eliminate those really stubborn square roots from our equations.
And this brilliantly illustrates one of the absolutely cleverest tricks in the entire toolkit. This is the universal trigonometric substitution, sometimes called the Weierstrass substitution, where t equals the tangent of x over 2. When you use this, a seemingly impossible, messy mix of sines and cosines is rigorously converted into a perfectly integrable rational function. It literally transforms trigonometric chaos right into manageable algebra.
Section 4. Geometry and Real Applications, Building with the Toolkit.
Okay, so we are shifting focus again, this time from pure algebraic manipulation to actually deploying our tools out into physical space. Our toolkit now allows us to find the exact bounded areas between multiple complex curves. We can calculate the volume of a 3D rotated solid using the disk and shell methods, literally calculating the volume of an object by sweeping a 2D curve through three-dimensional space. It's wild to think about. And by using derivatives and integration together, we can measure the exact, true length of a bent wire or a sweeping mathematical curve, which we call arc length.
Finally, Section 5, Beyond Basic Calculus, the Horizon.
We've mastered the core tools, sure, but let's tease some of the mind-bending concepts that lie just beyond standard single-variable calculus. First up is Taylor series expansions. This teaches us that complex, winding functions, like a sine wave or an exponential curve, can be perfectly rebuilt using an infinite sum of simple, basic polynomial terms. By taking higher and higher derivatives, you can construct a polynomial that just beautifully wraps itself around any function.
Next, we have improper integrals. Calculus miraculously allows us to calculate finite bounded numbers, even when our curves stretch infinitely far along the x or y axis. Imagine painting a fence that goes on and on and on, but then finding out it only takes exactly one bucket of paint to finish the job. That is the magic of converging improper integrals. And then, of course, there's L'Hopital's rule. So the crucial point here is that it uses derivatives to evaluate limits that initially appear completely mathematically broken. When you plug in a number and get a weird indeterminate form, like 0 divided by 0 or infinity divided by infinity, L'Hopital's rule steps right in, takes the derivative of the top and the bottom, and reveals the true hidden limit.
We have covered a massive amount of ground today, essentially turning abstract equations into real physical geometry. But I want to leave you with this final provocative thought. We've done all of this on a flat surface with just one variable. So how do these single-variable tools adapt when introduced to true three-dimensional multivariable space? What exactly happens when our curves become surfaces and our areas become volumes across multiple axes? That is the next great frontier of math. Thanks so much for learning with me today on this explainer, and I really hope this sparked your curiosity to keep exploring.